Hello everyone. In this video, I'm going to talk about recovery of rare earth elements from mine tailings. Rare earth elements are critical elements that are widely used in various industries, including fighter jets, electric vehicles, and all sorts of magnets and wind turbines. So, as a result, those rare earth elements are critical. So, in this video, I'm going to talk about that we have developed a novel process for recovery of high purity rare earth from mining tailings using a sequential leaching and solvent extraction process. So, in typically rare earth elements are present in mining tailings in the order of few hundred to few thousand parts per million, which is very dilute. After the excavation, the rocks or the mining tailings are grinded and comminuted and broken into small parts and goes through beneficiation and sieving. As a result, the concentration increases close to 2 weight percent. And so these rare earth elements uh, has both light rare earth elements and heavy rare earth elements such as dysprosium, light rare earth such as neodymium, praseodymium. And so these feedstock we dissolve into a nitric acid, and when we dissolve it, not necessarily all those elements are dissolved. uh, so we develop a sequential dissolution process, so we can directly dissolve into mineral acid, or we can dissolve in multiple stages. We found that dissolution in multiple stages is better than direct dissolution. So let's say we have the mm, feed solution or feedstock we dissolve into nitric acid, and not all those or ores goes into the solution, some remain as a solid, and whatever is goes into the solution we change, adjust the pH, let's say 3.2, and then some precipitated out. Interestingly, what did not dissolve or what precipitated out in this here, those are rich in the rare earths. What got dissolved is the rare earth doesn't get dissolved into there. Most of the non-rare earths such as calcium, iron, phosphorus, those get dissolved easily, and non-rare earth uh, precipitates out at higher pH. And then so as a result it goes concentrated, and then we dissolve into further into another acid solution. As a result we get a solution which is close to 4 times higher concentration compared to the initial feed solution. For example, initial feed solution about 2.4%, and after successive or sequential dissolution we got about 10 weight percent rare earth element. So we concentrated just by sequential dissolution processes, and now it has both rare earth elements, still also has non-rare earth elements. For example, 90% is non-rare earth, only 10% is rare earth elements. So it goes to further separation processes. We use a solvent extraction using a extractor. It's called Cyanex 572. It's a mixture of phosphorus and phosphinic and phosphonic acid based extractant, and that extractant extract heavy rare earth such as dysprosium, but also it extract iron. So, and then from this solution it goes to another extraction process using extractant tributyl phosphate or TBP, and the TBP selectively basically removes iron, or basically it extract iron but leaving behind heavy rare earth rich strip solution. And on the other hand, that but its composition is almost close to 60 percent heavy rare earth in this solution. And then the raffinate from the first stage of Sinex 572, we use another extractant which is called DEPA, diethyl hexyl phosphoric acid, and that extract the light rare earth elements, leaving behind calcium or other elements. So this solution is also close to 90%, so 60%. So this solution is also close to 60%, which is rich in light rare earth elements, and this is also close to 60% heavy rare earths. And separately, both solutions we precipitate using an oxalic acid solution. When we add oxalic acid, it it selectively react with the rare earth, both light rare earth as well as heavy rare earth. So from these two solution resulted in two precipitate or product. This is light rare earth elements. Its purities, total purity is about 94%, and it has 92% or 92.8% light rare earth and rest of the heavy rare earth, but total rare earth content is about 94%. Whereas in this solution we have got about 92% heavy rare earth and total rare earth is about 95.7%. So from this sequential leaching and extraction we have got about 95% pure rare earth from about 2.4% rare earth. So this is a great success that we can produce high purity rare earth, and we have also process for further purification. If we add another stage, we can recover from 94% or 95% to 99.5%, which is basically the magnet grade product. So this process highlights that we designed a process for low grade rare earth resources such as mining tailings, and the process reduces waste and supports sustainable resource recovery, improve domestic rare earth supply resilience, and this is a scalable flow sheet with clear path for optimization. So the key results are sequential leaching enriched rare earth elements in solution and reduced impurities, improving downstream separation. Synex 572 extract and selectively extract heavy rare earths and iron over light rare earth elements, and using tributyl phosphate effectively removed iron from the heavy rare earth rich stream, and DEPA removed light rare earth elements from the raffinate with high efficiency, trade-off observed with calcium co-extraction at higher extractant availability. And using oxalate precipitation we got two products, both are about 95% pure. One is heavy rare earth, another is light rare earth, and currently we are working on adding another stage to basically recover 99.5% pure rare earth elements. So we reported these results into in separation and purification technology journal. So thank you for listening. I hope you enjoyed it.